So, dear colleagues, dear guests, can you hear me? If okay, please type okay. While we are waiting for our audience, let me say a few introductory words. First of all, my name is Dmitry Kuzevanov, and I'm the head of one of the divisions of Russian Research Center of Construction, which today is the host and I would say organizer of this online event, of the online meeting. And the division that I'm leading is also well known and in Russia and in the world as Russian Research Concrete Institute, NISP, with a long history. And you know, it's a great honor and responsibility for me, of course, but there is an important part in my CV that I'm also very proud of, and this is, I mean, the membership in the International Federation for Structural Concrete, NFIB. NFIB, this is an association and I would like to say community of leading scientists and engineers from around the world, and one of the very important projects for my mind of this organization is the organization of a special commission for young engineers. It's called FIP Young Members Group. But you know, the word young is rather flexible word, and at the moment now we have a limit for age about 40, as far as I remember. And this commission, or the international group, if you prefer, was created in NFIB in 2017. And it was like a bridge between the new and experienced generation. And in 2018, we had a meeting in Prague, and as a result, many national groups were created. And in this picture, you can see national leaders and key participants of this international meeting. In this picture, you can see Spain, Norway, Czech Republic, Great Britain, Malaysia, Indonesia, Switzerland, Serbia, and others. And you know, I would say that after this exact meeting, the active work of Russian group began. And you know, during the time, we created active community in Russia. We organized many meetings and many discussions and workshops last year. And these pictures from our reports of our group, and we discussed different topics during our workshops. We tried different formats and we discussed fiber reinforced concrete, FRP, cold joints for concrete, new robotics and digital technologies, and so on, so on. You know, we discussed research and publications from the FIB Structural Concrete Journal. We tried different formats, yes. And you know, we have organized format, and I would like to say that it was convenient enough for everyone to discuss interesting question, and we tried different formats, like 2 hours after work, like short seminars, and it worked rather well. Colleagues from other countries also worked actively, and here's you can see the YMG Serbia activity. Fantastic work, and you know, we wanted to hold a joint meeting last year, and we discussed how could we hold such meeting of the Serbian and Russian group. And we were while we were discussing, you know, unfortunately new times have come, and new times that requires us to stay at home, and most likely no events will be held until September. Such new circumstances. But fortunately, I suppose new technologies and ways for communications and we have, and today, you know, today we want to just to test this new format of our work, like an online workshop. The truth is that what we came up with a local event for two groups, for Russian and Serbian group, I would say rather quickly became international one. And today we have more than 100 participants. I can see how at the moment here is the 70 online participants here. And you know, people from all over the world. And if you look at this picture, you can see that our audience today is, except Russian and Serbian group, includes Germany, Spain, Great Britain, Finland, Sweden, Norway, Malaysia, who else, so on. Yeah, and you know, the truth is that we have rather wide audience from academic and industrial sphere, from industrial fields, and I would like to welcome everyone here, and I would like to say that this is really an online event in the spirit of the FIB. When we create the bridge between research and practice, and this is a slogan of the FIB. And I would like to introduce and give a word to the most important, one of the most important person of the FIB, David Fernandez Ordenas. David, it's the word for you. Could you join us for the air? David?
I am. Here I am. Can you hear me? Yes? Okay.
Yes.
Thank you very much, Dmitry. I'm very happy to be here. Thank you for organizing this great event. Very nice. I mean, you and the Russian group of young members and not so young members, you're doing a great job. And I'm very happy that you can organize this webinar. This is really, really great. Today we are all of us having problems with traveling, and I think this kind of meetings, that can be meetings of groups or meetings of presentations like this, are going to be more useful. Maybe we'll have to mix them, the in-person meetings with the webinars, and I think it's going to be a very good thing. And from the FIB, as you say, we are very happy to incorporate young members, interested persons, and I think that the message from us is that don't be scared. You can be working together with the older people, the more experienced ones, and a mix of people is very good always. And I would tell you that I think that it's very important to incorporate the work of the task groups, because that's the way that when you are in there, you see the incredible benefits that you have by sharing and being with people that have different experiences. And I think this is really interesting. One very good example is Nikola, because he has been incorporated in some groups, and now he's working with these persons. He's working with the model code, the new document that we are preparing for the normative, and this is a good example that any interested people that want to work, it's really important that they can do that. And I want also to say that we are really willing to share the documents and to share the information that we have. We do it in several ways. Of course, we have the different kinds of membership, but this week we have put online for our members to be able to view more than 500 documents. that have been created in the FIB from the 1950s. So I think we are trying to put the information close to that. Some documents are only for members, but there are also many free documents there. So if you want, go to the website, try to look at there, and I'm sure that you will find things that you will be interested in. We also try to share information among us in the social media, and I hope that after this successful webinar, maybe we can post the video or we can share it with other colleagues. So I will be happy to hear any ideas. I'm going to tell you something that we are working on. It's not approved, but we are working on something that it's like a mentor program in which younger engineers can connect to older engineers, and they can, let's say, create a small partnership to share information, to share experiences, to see how to do things, and let's see if we can do that in the next times. But we are really wanting to incorporate people, and anybody that wants, they are able to do that. Dmitry knows this, Nikola knows this, and maybe some of the people that are listening can do that. So happy to be here, happy to say hello, and congratulations again to Dmitry and all his group. So I'll be listening to Nikola in the next minutes, and happy to answer any questions from you. Pass you the word. Thank you.
Thank you, David. Before we start our workshop, I would like to propose the following principle for attendances. If you have a question, please try ask it in the chat mode immediately, and if the speaker sees him, he will answer. And if he misses your question, I suppose you can use the special feature of this webinar platform, the questions mode, the question sections in the upper right corner. And I will try to help the speaker in the discussion and maybe comment something along the way. So in any case, it will be our first experience. Let's try to make it interesting. And I would like to introduce and invite our, I'm not afraid of this word, keynote YMG speaker, Nikola Tošić from Serbia, from Spain. And this is our joint event. Nikola, hello, how are you?
Hi, Dmitry. Hi, I'm great, thank you. And it's really an honor and a pleasure to be here. First of all, I hope you're hearing me well. Am I okay? Yeah, okay. So it's really amazing looking at your slides and looking back at the times since we first met and started this joint work through the FIB. It's been quite a journey, and it's great that even under these circumstances we come together even more. And so yeah, very happy to do this as the first of many events. So as you said, this is us trying some things. So yeah, I ask for the audience for patience and understanding for anything that we miss, but I hope we'll try to make it as interesting as possible. So thank you again to you and David and your group.
So it's your time. Okay.
Okay. So I'm in control now here. Thank you. So yes, as you said to the audience, please send your messages. I'll check from time to time. If something slips, we'll collect them for later. So we want to make this as interactive as possible. So we were talking about making the event and then doing something that's interesting for everyone, interesting for me to present, for people to hear. And we chose the topic of deflections, of reinforced concrete members, as a kind of topic that maybe we shy away sometimes in design, or a lot of things are maybe not clear. So this would be a kind of overview, but more importantly, I want to present like worked examples, so really some numerical examples and calculations, so that we can go a bit into the nitty-gritty, as they say, and clarify some things live as we go. So here. Okay, we're going to have just a brief introduction. There's going to be just a general overview of the problem of deflections, of deflection control, and of modeling. Then some theoretical background, then different methods that we have and that are being developed. Then one example calculated using several models, and then we'll comment on the performance of the models and what seems most time efficient to you. And talk about, of course, challenges ahead, because this is a topic that has a lot of still unanswered questions, and things in some areas are still difficult to overcome. So the introduction will be very brief. I want to introduce myself just in one slide. So I'm currently a Marie Curie Individual Fellow at the Polytechnic University of Catalonia in Barcelona, in Spain. I'm working with Professor Albert de la Fuente in the research group on sustainability and fiber-reinforced concretes. We go also some time back through the FIB. It's also a connection that was started through the FIB. And just this year, I started working here, and this project that is going to be focused on fiber-reinforced concretes, but also includes some time-dependent behavior of these concretes, and among those, of course, deflections. Before that, I was for a couple of months a Fulbright visiting scholar at the University of Notre Dame in Indiana, and there actually I developed, worked on some material models for time-dependent behavior in OpenSeas, an open source software, and I'm going to actually present an example of that today. And before that, I got my PhD and worked at the University of Belgrade's Faculty of Civil Engineering. So, as David said, I got involved with the FIB 2 years ago through the foundation of the Young Members Group, and then the International Young Members Group. Then now we have the Serbian Young Members Group, and I'm working in Task Group 2.1, Serviceability. And this directly actually deals with this topic for the new model code. So this is one of my interests. Others are these what we call like green concretes with recycled and waste materials, and now moving more into fiber-reinforced concrete. Okay, so sorry. Yeah, so let's start with the introduction. So as I said, like this is a topic that perhaps has been maybe slightly overlooked in design, or we tend to use simpler rules and somehow always check for serviceability. And among it, deflection control is one of the most important aspects. But why do we have reasons for limiting deflections at all? We have mostly two. One is appearance of the structure, and the other is function. And function, it can be like integrity of non-structural parts, like partition walls, but also functioning of some equipment of the structure. And as I said before, we would, traditionally you would design for ultimate limit states and then just check for serviceability. But over time, serviceability limit states and deflection control have become, increasingly important. And for this, there are several reasons. Over the last decades, we had globally a reduction of safety factors. We had refinement of ultimate limit state design, allowing us to save more and more material and make more and more materially efficient structures in form and material use. The structures have seen an increase of their strength overall, but usually this increase of strength is not accompanied by an increase in stiffness. So, even looking at, tabulated values for concrete properties, going from C30 to C80 doesn't give you a corresponding increase of the modulus of elasticity. So your stiffness is not going to increase as much as your strength. So you will satisfy the ultimate limit states more easily, but serviceability is going to remain a problem. And of course, there have been, economic and, let's say, aesthetic architectural requirements for increasingly larger spans of buildings, shorter construction times, which means earlier loadings of structures. And all of these means more and more problems for challenges for serviceability. So, roughly, we could say that today structures are, several times more flexible than 50 years ago. And that's why it's, becoming increasingly important to, be able to confidently calculate serviceability limit states. However, even though all of this is true, deflections of reinforced concrete members are influenced by many parameters. Really, a lot of parameters are influencing, and they are listed here. So, they are the geometric properties of the member, the shape, size of the cross-section, of course, is going to influence the, as I said, stiffness or modulus of elasticity of concrete, but reinforcement as well. Then the concrete tensile strength, because this is going to be also determining cracking or not. Then, in concrete structures, we have a redistribution after cracking. Then the amount and placement of reinforcement, we all know whether we have compressive reinforcement or not, how much tensile reinforcement we do. We only adopt as minimally required for ultimate limit states or more. Load history and stress level in the material. So, stages of construction are going to be increasingly important, especially for those early loading times of structures. Clearly, the statical system and shape of the bending moment diagram, because this is what causes the curvature that causes deflections. Shrinkage and creep, again, which change a lot depending on ambient conditions, concrete, and also a lot depending on what you produce your concrete with. And this is sometimes not something that we can easily encompass with codes. We have to give something that is an average for a large database, but the variability of this is very large. And then another redistribution of influences due to creep and shrinkage themselves. And as there are many parameters, each of them is associated with a very high scatter. So this is all that is, making modeling of deflections, of serviceability, of in-service behavior very complex. Okay, so with that, we can move into a kind of theoretical background and methods that we have. So we said that, we limit deflections for appearance and function. So, how are these generally derived, and, are they precisely derived? From the current Eurocode, we have the following clause that says that appropriate limiting values of deflections, taking into account the nature of the structure, of the finishes, partitions, and fixings, and upon the function of the structure, should be established. So it is, straight away relegated to the, client and designer to agree, because it's such a wide topic that, you will, depending on your case, probably want some different deflection limits. But generally, when we're talking about appearance, what we want is to avoid a sense of discomfort, visually and physically, in a sagging slab. So based on studies, which are also from nearly 60 years ago, mostly in Germany, this limit was derived that says that the sag is limited to span divided by 250 for quasi-permanent loads. Okay, so these are loads that can be considered to be permanently on the structure, and they include, of course, all the dead loads and a part of the live load, which can be turned to be, as if it was always there, which is again some kind of statistical modeling of the load, but this is how it's taken through the code. And then there is this relative to supports, okay, and this is the bit also can be, ambiguous. So, when we're looking at a flat slab like we are here, and I think I have my pointer here, okay. So relative to the supports can mean, of course, then several things. The easiest would be relative to the columns, which are clearly a support for the slab, but then, you're limiting to a span, which is the diagonal, okay, divided by 250, which is a kind of bigger value, but then you are considering the total deflection that is happening here, Vmax. Or you can consider this strip, let's say this horizontal or vertical ones. Then you have a shorter span. So you would say, okay, it's a shorter span divided by 250, but it's also, again, now not this deflection. So here you would have to compensate for the kinematic displacement of the ends of this point here and this point here, because you only want the deformation part of the deflection. So this is also something to take into account. It's not the total displacement. It consists of two parts, kinematic and the deformation part. One is from the displacement of these strips here, and one is from the deformation of this strip itself. Okay, so there is already we are in a kind of interpretation and ambiguity. So we have to take care of that. The other, as I said, is impairment of function, which can literally mean functioning of equipment. And this is an airplane hangar in Belgrade at the Nikola Tesla airport. It was built in the 90s, and its system is interesting because it's a two-belt system, with a tension cord that is from pre-stressing tendons and a compression cord here. So what function means is if this would have a large deflection, then this straight line that is necessary for the sliding door would become this deflected red line, and you would lose function of your hanger. You would not be able to open the door. This is one point. Maybe it's less common when we are at least talking about buildings. The more common part is the damage to non-structural elements. And of course, okay, we can talk about if masonry infill is a structural part or not, but generally deflections can cause damage to them. But here we are talking about something that is called deflection after construction, okay? Because the partition wall is not built at the same time, of course, as your concrete structure, only later. So only a part of the deflection is something that affects your partition. So starting from the installation of your partition wall onwards is what you consider a deflection after construction, and this then has to be limited to span over 500. This is again a recommendation in Eurocode, and so you have to calculate basically two deflections at least. One, the long-term deflection, and then subtract everything that happens until you install the partition wall, and then this increment has to be smaller than 500. And you can see here explained like what are the mechanisms by which this damage occurs. So if this slab, which is holding up the wall, deflects, what's going to happen is part of the weight above is going to be transferred through this arch, but this part here is going to be pulled down with the slab, and the connection is going to break, and you're going to have cracking, or also here from the inclination between the strut and this part here. So we want to limit deflections in those cases. And here, of course, I'm going to limit myself in the rest of the talk to buildings, to generally slabs, because this is kind of the majority of structures that we're dealing with, and for which we can most easily codify things and recommendations. Of course, going into different structures as bridges, I think it's going to be a lot different, but here, at least within this lecture, I'm going to be focusing on these reinforced concrete applications and buildings. Okay, so we talked a bit, but just to formalize, the types of deflections that we have are these what we call initial, or sometimes you'll hear instantaneous, or sometimes you'll hear immediate. And this is also something that you can discuss looking into experiments, at least how people define it. It can mean a deflection that is 1 second after applying the load. It can mean a deflection that is 5 minutes, 1 hour, 1 day after applying a load. So it carries with it a certain also uncertainty, but at least a comforting thing for building is that we're not so concerned with this initial deflection, for limiting that. We are interested in the long-term deflection. And it's this total or, final or long-term deflection that has this instantaneous component, and then the increment, which is long-term or time-dependent. So that then happens an addition due to creep and shrinkage. And then you can separate, combining these two, deflections after attachment or installation of non-structural elements. And then this is what we talked about, which would be the total deflection, or at some time, minus whatever occurred until we installed this non-structural part. Considering loads, again, at least for buildings, we're going to be dealing with mostly two combinations of loads. They're all serviceability combinations, so safety factors are going to be one. It's going to be the mean or mean value for the dead loads, or a upper characteristic value for the live loads. And we have the quasi-permanent combination, which again has all of the dead loads, but also a fraction of the live load. And usually it's 0.3, let's say. So we consider 30% of our live load as if it's dead load. So, live load is a variable thing, but when you average it over time, over 50-year life of the structure, it's as if 30% of it is always there. And there's the characteristic load, which is, all of the dead loads, then one dominant live load in its full intensity, and the others with its characteristic C coefficient in the combination. So this is a kind of maximum service load that the structure can experience within its lifetime with a certain frequency of, let's say, 5%. So yeah, these are the two combinations that we're going to need for buildings. Of course, as I say, for bridges and other specific types of structures, these can be different, and of course include traffic loads and so on. This is for modeling the load parts. For modeling material properties, again, Eurocode at least says the calculation method adopted shall represent the true behavior of the structure under relevant actions to an accuracy appropriate to the objectives of the calculation. So, important thing to note here, at least in Eurocode terminology, is this shall. So this is kind of the hardest statement that you can have in Eurocode, which means you must do it, like you shall represent the true behavior of the structure to an accuracy appropriate to the objectives. So now comes, the interpretation part. So, the objectives are the appearance and function. And what is the accuracy? We're going to get back to that later, but you have to consider all of those influencing parameters and their scatter and variability. Basically, what this means is that since we are in service behavior, we're going to be using mean values for properties of the materials, or our best estimates, let's say. So if you have measured values, it's going to be average measured values. If you're designing, it's going to be the mean compressive strength, the mean axial tensile strength, mean modulus, and so on, creep coefficient and shrinkage strength. So next, we have to know how we're going to model our concrete behavior, and for that we need to know at least closely what is the realistic concrete behavior. So concrete behavior is initially, when you start increasing the load, going to be linear, of course, and it's going to have a stiffness, a response to load, here is deformation, that corresponds to the uncracked stiffness of the structure. So it's the full concrete, okay, the uncracked concrete section, the gross concrete properties, or if you want, you can also consider a transformed section, so taking into the effect the stiffness added by reinforcement or tendons, if you have them. But once you reach the cracking load, of course, one section cracks first, okay, then another, and so on. So you gradually have a discrete reduction of stiffness in certain sections. So in a certain number of sections, in the sections themselves, you're going to have a stiffness that is highly reduced. That is the stiffness of the fully cracked section, okay? And if the entire beam was fully cracked, so only composed of the compressed concrete and the tensile reinforcement, you will have this kind of response. But of course, you're never going to have a fully cracked section, because you're always going to have something in between the cracks. You always reach that maximum, that state of developed crack state where you cannot open new cracks. So you always have some concrete in between that does not allow you to reach this response, but something intermediate. But you approach it gradually. Okay, you start after cracking from the uncracked response and asymptotically go towards the fully cracked response. And then at higher loads, let's say above concrete stress is above 60% of the compressive strength, you're going to enter into a further nonlinear behavior and the ultimate load. But in service, you're going to be here in phase 2, or even more problematic for slabs in buildings. In service, you're going to be actually very close here to the cracking load. So this will cause an additional large uncertainty, because if you are slightly under your cracking load, this is your deflection, but a bit above, the deflection is twice as large, 3 times as large. In any case, this means that our true behavior is somewhere between these two responses, and we have to find a way to figure out where we are between them for each load. So we actually have to model this behavior between these two lines, and that's what all of the models attempt to do. What this translates to is this kind of thing. So on this figure, okay, a simply supported beam, let's say under uniformly distributed load, what happens at T0, once the beam is loaded and a certain zone of it is cracked, and it's indicated here, which means that the bending moment diagram, supersedes the cracking moment here and here. The curvature of an uncracked section, so the curvature, which double integrated is going to be the deflection, is this line here. It's a small curvature. But in the cracked zone, you know, going back to the previous slide, the response of the fully cracked section, it's going to have this curvature here, the larger one. And in reality, the real mean curvature between in the cracked zone is this dashed line here. What happens over time is that now we have the effects of creep and shrinkage that further increase this curvature. Why? Because they increase the strain in concrete. So looking at the cross section here, you start from a concrete strain, which is here, epsilon c at T0, and this is your neutral axis here, and this is your cross section, your strain line. Over time, this epsilon c, we're going to see a relationship later, has the initial strain, which is this what we have here, but now it's increased for creep and increased for shrinkage, so it goes all the way up to here. Okay, and now our strain line is this. The curvature, of course, is going to be the sum of these two lines divided by the effective, the strain in concrete and in reinforcement divided by the effective depth. And we see, of course, that because of the bigger strain in concrete, it's going to be a much bigger curvature, both in states 1 and states 2. Okay, so this is a new curvature for state 1 and a new curvature for state 2, and the interpolated. Also, what happens is, maybe here I should have kind of pointed it out, that the cracked zone is going to extend as well. Here, it's wider than it was here. So new cracks are going to open over time. Why? Because basically shrinkage is going to eat up your tensile strength in parts of the concrete and open new curvatures. So you'll see also in modeling how this is achieved. There is an over time a reduction of your cracking moment. So this is the, let's say, mechanical behavior at the level of the cross section. Here, yeah, this I should have told you. I've put here numbers that you can see in brackets. These are references that you'll have at the end of the presentation. So it's going to be literature to look for further reading. So here, okay, focusing back on the cross section, we should note a couple of things. First, this is the, we said, strain line at T0, and then there is an increase of the concrete strain, but a very slight increase of the steel strain, practically remaining constant. So basically the rotation of the strain line happens more or less around the reinforcement, and this is the increase in the curvature due to creep and shrinkage. What is important to note is here is the change in stress. So we are starting from this diagram here, a large stress in concrete, okay, until this neutral axis, which corresponds to the neutral axis of the strain line. So the point of zero strain corresponds to the point of zero stress at T0, but over time it does not. Okay, so zero strain is here, but over time zero stress is here, and these 2 points don't correspond because this total concrete strain has a stress-dependent part, which is the initial and creep, but also shrinkage, and it can also have thermal strains. So these two are not going to match. And also importantly, you're going to see this lowering of the neutral axis. This is even something, reported in the experiments, that you have this shifting down of the neutral axis. Okay, so going forward, how do we model all of this behavior? So we can do it in several ways and several levels. The also Model Code 2010 introduced this, but not for all aspects, but the Model Code 2020 is going to introduce it also for serviceability and for deflection, what we call levels of approximation. So the higher the level of approximation, the higher the complexity and should be higher precision and accuracy of the model. But it should, going back to the recommendations of Eurocode, correspond to the necessary accuracy that you're searching for. So generally, we're going to follow 3 levels of approximation, and in decreasing order will be the decreasing complexities of the model. The level of approximation 3 are what we call general methods, and they're called this way also in the current model code. So I put here the entire paragraph. We don't need to read it, but generally, at least the bold parts are going to point out to you that these general methods, as their name suggests, need to be as general as possible. So they need to be able to perform a nonlinear analysis, okay, and this instantly will preclude it for a lot of the problems, okay, because it means it's much more complex. to calculate the instantaneous and time-dependent deformation, and we need to be able, with these methods, to take into account the effects of applied loads and pre-stressing, the nonlinear behavior of the materials, okay, and the time-dependent deformations due to creep shrinkage and the relaxation of pre-stressing steel. These methods in general, of course, because they're nonlinear, need to be iterative and incremental, and they also need to be able to perform a step-by-step analysis to model the sequence of loading, any changes in geometry like phased stage construction, the structural scheme, the changes in support conditions over time, and preferably the evolution of material properties over time. Okay, so this is going to be anything you can think of that is happening to the concrete, you should be able to model it with the general method. What this actually means is that for this we need nonlinear finite element analysis. Okay, and this can be this like commercial software like the ones that we all know, ANSYS, Daena, Athena, Abacus, all of these, name it, whichever that has material property, these capabilities. But also, I mean, at least for researchers, open source software. And here I'm mentioning OpenSeas because that's the framework within which I developed a model, and I'm going to show it later. This here is from the FIB Bulletin 92, and this is the CONS software developed by Professor Toni Marie here in Barcelona at UPC. And it is a general method, so you need capabilities that discretize your cross sections into layers or filaments. You need to be able to assign, complete degrees of freedom to the elements and the nodes, nonlinear behavior of concrete, nonlinear behavior of steel, and so on, and then conduct this iterative procedure that solves, for everything. Further, also within the general methods, we have something that is not based on nonlinear finite elements, but is a kind of, let's say, for me, level of approximation 3B. So it's a notch below these. It's the all famous Seta method of integration of curvatures. So it's called Seta method based on that distribution or interpolation coefficient that actually does the modeling of where we are between states 1 and 2. And it's a general method, it has general applicability, but some things are more difficult in it than others. So what this does is discretization of the concrete into discrete lengths that are assumed uncracked and fully cracked. Okay, so basically in reality, between two cracks, you have some tension stiffening, which is the contribution of concrete between the cracks to tension, okay, because not everything is fully cracked. But, we cannot do it precisely for each point. So what we say is, on average, we're somewhere in between. So how do we get to this average? By saying that some parts are assumed fully cracked and the remaining part is assumed uncracked. And then when we average these together, we are somewhere in the middle or closer to one and the other. So this is the distribution coefficient Seta, which is between 0 and 1. When it is 0, then we are at the uncracked stage. When it's 1, we are at the fully cracked stage. So it's as if we said that actually these parts are, Seta times S half, which are fully cracked, and this left in between is assumed uncracked, okay, for the crack spacing. This is then also transferable to different variables that can be interpolated. We can interpolate strains, as we have here. This is the mean strain in steel, which is interpolated in the following manner. Of course, here again, we have a line that shows the crack and the crack. This is the part that we assume uncracked, as well as this one, and what we assumed fully cracked. So the real behavior, the real development of the strain between the cracks is this. Epsilon S2 would be this value here at the crack, epsilon S1, this value here, that is for the uncracked. But interpolating, we get this block behavior, okay, instead of this. And because we can do it to strain, that means that directly we can do it to curvature, of course, because it follows directly. So the mean curvature is going to be just the Seta distribution coefficient times the curvature in the fully cracked states, and 1 minus Seta times the curvature in state 1. Okay, what is the Zeta coefficient? What's its formulation? Is this. It's 0 if it's an uncorrect section, of course, because we're not interpolating anything. But if it's a correct section, then it's this formula. 1 minus, again, a coefficient beta times sigma SR divided by sigma S squared, okay? And within here, we have first beta, which is an empirical factor, which is 1 for first loading and 0.5 for repeated or long-term loading. Okay, what does this mean? So when beta is smaller, we get higher Zeta coefficient. So we're closer to state 2. Basically, this 0.5, you will see later when we move into moments, represents the gradual reduction of the cracking moment over time due to shrinkage, and the fact that over time we are more and more approaching state 2, as was shown on the previous image. Actually, images, if I just go back. Here, the fact that we had increasing curvatures and see, the distance from state 2 here is bigger than here. So over time, we're going to move closer to state 2, and this is going to be represented by the decrease of the beta empirical factor from 1 to 0.5. Now, this 1 is actually also, first loading, when you're sure that your structure is not cracked for the first load. So all in all, a recommendation could be to just always use it 0.5 and be on the safe side, but theoretically, yes, it is formulated as 1 or 0.5. The stresses, this sigma SR is later going to be replaced by the cracking moment, but here is the tensile stress in reinforcement calculated for a cracked section. So this is important. So you calculate it for a cracked section under cracking load. Okay, so basically at the cracking load, you have a response, infinitesimally before, which is with the uncracked stiffness, or you have it afterwards. That's the jumping curvature that you usually see on moment curvature relationships. So this you calculate with the cracked section stiffness and precisely under the cracking load. And this is going to be your tensile stress for your load, basically. But we'll see also later, it's going to be for the maximum load that you can have in a structure. Okay, sorry. So continuing later, how do we take other things into account in this Zeta method? Creep. There are more complex ways of taking into account, like Volterra integrals and so on, but can be solved for a limited number of cases. The most common way is through the effective modulus of elasticity, which is the modulus of elasticity divided by 1 plus the creep coefficient. And okay, we're going to talk about here the choices of creep coefficient, but basically this is the formulation. What you can do for buildings, for example, when you're doing some more simplified analysis and not wanting to model stages of load application, is you can use an effective creep coefficient. So you have your live load applied at, 40 days, your additional dead load at 60 days, and maybe your live load at 180 or 360. But to apply it all at once, you would say, okay, it's as if I was loading everything at 28 days, but all of the load I am modeling with this effective creep coefficient, which is now each load times its own creep coefficient that now depends on the time of loading of that particular load divided by the total load. So it's just a kind of, centroid of the creep coefficient, and then it's a single creep coefficient. It's going to be useful for simplified models, but of course not for the ones for the general method where you want, stages of load application. Now, another important factor, the question of pairing the creep coefficient and modulus of elasticity, and this is often brought up in papers and documents by Professor Barjant, if anyone is reading them. It is the fact that describing the evolution of strain, the stress-dependent strain, you model it by so-called compliance function. So for a constant stress block, the evolution of strain, of the stress-dependent strain, is linearly dependent on your stress for what we call a linear creep. and this is for loads up to, let's say, 40% of the compressive strength. The strain response is linearly proportional to stress, and this proportionality is expressed through the so-called compliance, which has two factors, and these can look differently. In the model code formulation, it is like this. It is 1 over modulus of elasticity at the time of stress application, and so it is ECT 0, okay? So if it's loading at 14 days, this is the modulus at 14 days. And then it's the creep coefficient divided by the modulus of elasticity at 28 days. And this creep coefficient in the model code is supposed to be the creep coefficient calculated according to the model code model. So when you're using that, you should always combine it with the 28-day modulus of elasticity, okay? That's important because you can have your experimental creep coefficient, for example, which is just going to be creep stress divided by initial stress. And it's going to be different if you would do that. Your experimental creep coefficient would here also have the modulus of elasticity at T0. For example, the ACI formulation in the 209 model for shrinkage, for creep, sorry, is the same modulus of elasticity here. So it's wrong to take a creep coefficient calculated by ACI and plug it into a compliance that is from model code. So these are things that should be taken into account. So what's important is the compliance, because in the end, it's what gives you the strain. But within it, you need to be careful of which values you are pairing together. Okay, so when we're dealing with the model code, if we calculate the creep coefficient according to the model code, we need the modulus of elasticity here at 28 days. Okay. I'm a bit worried, honestly, that I don't see any questions so far. So I hope at least someone will be the icebreaker. I don't know, Dmitry, do we have any questions? No? No? Okay. Okay. Going forward, we covered creep, now shrinkage. So, okay, sorry, from creep, we get the curvature from loads, which is basically just the moment divided by bending stiffness. But here we have this effective modulus, okay? So M over EI. And this moment of inertia is, let's say, ideally should be the transformed moment of inertia for states 1 and 2, which means taking into account reinforcement through the ratio of moduli of reinforcement and concrete. Curvature from shrinkage is explained here, okay, for, let's say, sections without compressive reinforcement. You would, the concrete would want to shrink, of course, but the reinforcement would not, so it gets compressed while concrete gets tangent. But actually here is, of course, the resisting force that causes an additional curvature. So, of course, if there was the same amount of reinforcement in a symmetrically reinforced cross-section, there would be no curvature from shrinkage, but this is not how we reinforce slabs or our elements in bending. We reinforce them according to the bending moment diagram. So, in 90% of the cases, there is a difference between the tension and compression reinforcement. Hence, there is a curvature due to shrinkage, which is like this. Okay, where this is the shrinkage strain, the free shrinkage strain, again, calculated, let's say, according to the model code 2010 model. This is the moment of area of steel, again, in states 1 and 2. Simply, it is the area of steel divided by the eccentricity. You will see in different places, different formulations. Usually it's written with an epsilon times alpha, which is the modulus ratio, and then S over I. But in that case, S is just literally the moment, the area of reinforcement times the eccentricity. But here, because I put this star here, it means it's already transformed. So the ratio of the moduli is already within S. You will see it later in the calculation. Okay. So thank you, Christina.
Everything clear.
Okay.
Nikola.
Okay.
No questions.
Okay. Yeah. Thank you. So calculate the curvatures in states 1 and 2 and in sections along member length. Okay, so this is the general application. So it is based on a section. So you need to divide your length into a number of sections. Sorry, Emmanuel says, what happens when the supports of the slabs are restrained? the shrinkage effect will have major impact on the number of cracks. Yes, and then this is something that your general method again should be able to take into account. Yeah, you will have to impose, we'll see later also when we are doing like this integration, boundary conditions on your model. Okay. Sorry, calculate curvatures in states 1 and 2 along the membrane length, interpolate and integrate them twice, because once we integrate curvatures to get inclinations, it's English, and then the second time to get deflections. In case of pure bending, and again, because I'm focusing on buildings, it's going to be pure bending, you can reformulate your Zeta distribution coefficient, not in terms of stresses, but moments. So that sigma SR becomes M cracking, and M maximum is the maximum moment acting on the strength. So let's clear up first that M max, maximum moment that can act on the section. So imagine you are calculating deflections for quasi-permanent load, okay? And in your cross section, the moment from quasi-permanent load is, I don't know, 10 kilonewton meters, okay? That's not what's going to go into Zeta. It's not going to be 10 here as M max. You're going to want to plug in here your characteristic bending moment for that section, which will be, let's say, 12. Okay, why? Because Zeta models the extent of cracking, and the characteristic load at one time during the life of the structure will appear. And once it appears, it's going to crack the structure more than the quasi-permanent load. But those cracks are going to remain even after the characteristic load is lifted and you're only left with the quasi-permanent load. So in order to model that fact and bring you closer to state 2, here you always plug in the maximum moment that can ever appear on your cross-section, okay? Which is not necessarily the moment under which you're calculating the deflection. So what you used to calculate the curvature here is, generally not going to be the same moment that you're going to plug in here. Okay, it's probably going to be the characteristic moment, that one that has, one characteristic load in full and the others in combination. Now, it is 0 when this maximum moment is less than square root of beta times MCR. So it seems as if we're not comparing with the cracking moment, but with the product of this. Why? Because just put this beta within the brackets here, it's going to become square root of beta, because here you're squaring, okay? And that is the fact that this beta is modeling the reduction of the cracking moment. Because when beta is 0.5 for the long-term deflection, square root of 0.5 is around 0.67. So that amounts to pretty much saying that over time you lose about a third of your cracking moment due to shrinkage. And for a variety of cross sections, you can calculate this yourself, okay? You can calculate relatively simply how much tension you are producing by shrinkage, and you will see how much you are reducing your flexural tensile strength. Okay, now this is another question, how to calculate the cracking moment. Okay, simplest way is, of course, you're going to use the gross section modulus, okay, but you can use the transformed one, taking into account the reinforcement. It's not going to be such a huge difference. But the question of choosing the tensile strength is also important. In some ways, it's an academic discussion only, but in some ways also it could be important. Naturally, like what you would associate with bending would be the flexural tensile strength. That somehow seems intuitively natural, that, with which strength does concrete resist flexure with its flexural tensile strength, right? But because these models contain some empiricism, for example, this Zeta distribution, they are also calibrated on some databases of results. And it seems that, when they were formulated, they were calibrated to give the best results when you plug into the cracking moment the gross section modulus and the axial tensile strength, the mean axial tensile strength. So far, that is what has been recommended, been mostly used. ACI before had its rupture modulus, which is basically the tensile strength, but they recognized later that you should not use the full rupture modulus because of the effect of shrinkage. So now also ACI says reduce rupture modulus to 2/3. And what does that mean? That's the 1/3 that you lose due to shrinkage here. They don't have beta, so it's a different way that they do it. So you can use FCTM, you can use flexural, okay, or you can use the reduced flexural. So take the full flexural, calculate how much is eaten up by shrinkage, and then use that. That seems somehow the most realistic and best option to use. But again, when you do those analyses, and there are those that were performed, it turns out that this FCT flexural reduce somehow ends up being very close to FCTM in reality. So you're back somehow to using one of those two would be my recommendation. Full flexural, very rarely. Maybe if you were curing the concrete until the day you loaded it, and then you say, okay, like I only had basic shrinkage developing, and in normal strength concretes it's very small. Otherwise, it should either be FCTM, keeping in mind that it's due to calibration purposes, or this reduced flexural strength. What's kind of time consuming here for this Seta method is that you have to do it sectional properties. First, you have to calculate them twice for cracked and uncracked states, but you also have to do it if anything in the reinforcement changes. So in a continuous beam, you're going to need to do it, at least 4 times, depending on how you're curtailing the reinforcement. But at least you have 2, let's say, distinct cross sections above the support and in the span, and for each of those you need to do it twice in the uncracked and cracked state. So that's, of course, it's automated in Excel, in MATLAB, whatever, but just to keep in mind on the computational requirements. And you need to develop an iterative procedure for indeterminate members. So, we said in the general method, we need to model that redistribution, whether it's due to cracking, whether it's due to redistribution from creep and shrinkage. So remember that deflections are the integration of curvature, which is directly dependent on the bending moment diagram. But is the curvature really the one that comes from the elastic analysis in statically indeterminate members? No. So you're going to introduce a large error if you just keep using the elastic bending moments for statically indeterminate members and integrate curvatures from the elastic distribution. So this is something that you need to take into account here. Okay, then we come to levels of approximation 2. So now, one step below. These are something that should be relatively more simple. And these are kind of simplified Seta methods. And they are based still on interpolation, but this time they are, as if we integrated in a single step, not in different spans, in different sections, but in a single step. So we interpolate deflections, actually. So we just calculate deflections from the section properties that we had in states 1 and 2 and interpolate the deflections, okay? So this is, of course, going to introduce an error, but there are ways for compensating for that. This is the expression when we are interpolating directly deflections, okay? There are several methods. Most famous one, developed again by the group here at UPC, Professor Tony Marie. And before, like in Model Code 2010, you had it stated kind of generally, like it's sufficient to calculate deflections twice and interpolate. Now, I'm guessing in the new one, it's going to be more precisely prescribed. So you're going to have really a procedure laid out, and I'm going to present that procedure later. Their procedure for calculating the deflections. So you're really going to have recommendations on you calculate, this equals that, and so on. What they do, because I said in the general Seta method, you need to calculate sectional properties for any change in reinforcement and so on. They recognize this, and then they introduce these effective reinforcement ratios. So there are these combinations. You have your rho C, which is the reinforcement ratio in the tensile part here. This is the part LC. You have this section, you have some reinforcement there, compressed and tensile, and here also. You have expressions that give you effective reinforcements. that give you an effective tensile reinforcement and an effective compression reinforcement. And this is what you use to calculate your sectional properties, because now you calculate only for a single section, and it's a kind of equivalent effective section. So this is important. And then, of course, there are ways to introduce creep, shrinkage, and so on. And we're going to see it in the example. Okay, there is the level of approximation 1. Here I'm not presenting. There also is like a newly proposed method, but only for long-term deflections, also a much more simplified method that will allow you to calculate long-term deflections. And it's probably going to be new Eurocode, new model code, new method. But there are also these, let's say, indirect deflection controls, or say, let's cases when you don't need to, when you need to calculate. And these are basically what you know as limiting span to effective depth ratios, L over D. And they were derived based on large parametric studies. Of course, you know, with any kind of formulation like this, it's going to be difficult to capture all parameters in a simple formulation. And yeah, there have been some challenges with using that. Probably the formulations are being changed. Because it highly depends on the choice of your parametric study. For example, if I recall well, like in the one that was done for the current Eurocode, a creep coefficient of 2 was assumed, a shrinkage strain of 0.4, but let's say I think a ratio of quasi-permanent to design load of 0.5, and in buildings it usually comes out as 0.62, for example. And then this means a bigger impact on the LD ratios and so on. So there were changes necessary there. And the recommendation is to use it as a preliminary check to somehow get to your slab depth using this, but then use one of these simplified, for example, methods to do a full calculation of deflections. Okay, there are parts in the code, I'm not going to cover them in detail here, concerning pre-stressed concrete, which is going to be much more simple. If it's uncracked, of course, then the curvature is just the bottom and top strain divided by the overall depth. And of course, here we see the relationship of the concrete strain. So it's the shrinkage strains times, yeah, this is the strain from pre-stressing, and then this is the creep coefficient at the time of pre-stressing. And then here you have the increment of stress. So up to the time when you're looking at it, you have an increment of stress, but then you're using the same creep coefficient with the aging coefficient, which is generally 0.8 or 0.9. Deflections due to shear, this is put as a question. There are situations, I guess, when this can be important, and there should be new methods, kind of graphical, also simplified approaches to kind of go through a normalization. So you go through your bending deflection, and then you would get your shear deflection from some graphs. And with this expression, you would be able to add the influence of your shear deflections to your bending deflections. Again, it's going to be for, let's say, sections with a thin web, pre-stretch sections, there are concentrated force, not a large number of situations where this is going to be important. Okay, now we get to the example and model comparison part. I'm conscious of the time, so I think we will be within the limit. For this, I chose something relatively simple. So I selected a simply supported beam from a very good experimental program, so where we have everything measured. And then we're going to do a comparison of 3 models of the general nonlinear finite element method, of the Seta method of integrating curvatures, and of a simplified method. And we're going to see, you know, you can judge the amount of time necessary and precision that you get. But of course, keeping in mind that here I selected a simply supported beam, so it's not going to be any effects of redistribution. And it's, again, closer to modeling a beam than a slab. And for slabs, you would have some things that appear differently, but I wanted to go through the numbers exactly, not just, you know, show graphs results. I wanted to go into the model itself and the calculation. So it's a simply supported slab. It's a program from the University of New South Wales, Professor Gilbert, who is really like a famous name in this field. In the program, they had beams and slabs. They had 6 beams, 6 slabs. I chose the first one to not be biased in some sense. They had the span of 3.5 meters. dead load, self-weight, and 2 additional forces in the thirds of the span. So this means that in this case, we only have 1 load. So, there is no application of a load and then removal. So we don't have a characteristic and quasi-permanent. We only have 1 load that is applied at the same time. And this is the cross section, 250 millimeters by 348 with an effective depth of 300 millimeters and 2 number 16 bars. Okay, this is the self-weight that we have written here, the loads, moments, and we just have the maximum moment that was 44% of the section resistance. Okay, so let's say that, yeah, the load is relatively realistic for service loads. Compressive strength was not so high, kind of cylinder strength of 25 megapascals, loaded at 14 days and cured until loading. So also important for the shrinkage that, let's say, except basic shrinkage, there was no development of shrinkage until that time. Modulus measured at 14 days and at 28 days. Tensile strength measured at the time of loading, okay, splitting, or we can approximate it to axial tensile strength. Reinforcement, which is a reinforcement ratio of 0.54%. So it's not really like slabs, but okay, it's not such a high reinforcement ratio. Humidity was generally 40%, and these were the final measured shrinkage and creep values. Final, I mean, at 380 days. The shrinkage strain, and this is when talking about the uncertainties of creep and shrinkage. Try to model creep and shrinkage with these inputs, with 40% humidity and these strengths, and at the same time get such a high shrinkage strain and such a low creep coefficient. It's a bit a strange combination, but just goes to show about the scatter of the results of these models. You would expect a concrete having such a high shrinkage strain to have a much higher creep strain, but that's just the result. Okay, so these are the inputs that we have, and these are the deflections. So, sorry, Dmitry, how do I remove? Sorry. Okay, never mind. No, because I'm seeing the strip with all the slides. It's blocking my view of the slides. Okay, I'm okay. Sorry. So these are the deflections that were measured for 380 days, starting from 14 until 394. So it was under load for 380 days, and it went from, let's say, 495, 5 millimeters, to 12.06. Okay? So a 2.4 times increase of the deflection over time. For a beam, it's as expected, and depending on the loading ratio. So the lower your load, the closer you are to the uncracked section, the bigger this increase is going to be. Because in a cracked section, what's going to creep is the compressed part, which is going to be increasingly smaller as you go to higher loads, and its effect is going to be smaller and smaller. So, okay, here we have from 5 to 12. For a lower load ratio, it would be more. In any case, here I'm repeating just the main data of the beam. And you see this I'm here showing in a linear time scale. There's this whole discussion to be had about showing time-dependent, especially logarithmic behavior in a logarithmic scale and so on. But I think for all of us, it's going to be clearer looking at it like this. So you see this kind of nice, logarithmic development of the deflections. Okay, first comes the general method, the nonlinear finite element analysis. And here I'm talking about OpenSeas, which is probably a lot of you have heard about it through earthquake engineering, dynamic engineering, object-oriented open source structural analysis software developed at UC Berkeley in California. And it's really a versatile software. It's hosted online. You can download it for free. Of course, use it for academic purposes, but you can add new code to it. You can add your models, your elements, your analysis procedures, everything. So this is what I worked on at Notre Dame last year. Professor Yaya Kurama, with a former PhD student, developed first some time-dependent concrete models back in 2012, 2013. Based on ACI, So the models had the ACI, creep and shrinkage, built into them. And later I updated them, added new models that had the model code 2010, creep and shrinkage formulations, and even had a fully nonlinear behavior. So before it was with some tension softening behaviors, but linear in compression, we added a fully nonlinear response for concrete, plus the model code creep and shrinkage models. So we managed to get even the code incorporated into the source code of OpenSeas. So now if you go from this website to GitHub and download the code, if you compile it in your Visual Studio or whatever you're using, you will get these models now with their functionality. And within them, we have this TD concrete, like time-dependent concrete, MC10, standing for model code 2010, NL, nonlinear material model. So as I said, with the nonlinear concrete behavior, which is given here with parameters, inputs that can modify this curve completely in compression and in tension, and give you creep and shrinkage according to model code 2010. Generally, the procedure, I mean, I'm not gonna spend too much time on it. It does what it needs to do. So it discretizes a section into fibers. It has an iterative solution procedure, and you use the kind of pseudo time steps that they already have in static analysis. Only now you switch some global variable on that it starts accumulating creep and shrinkage string. And this is the solution procedure, but I don't think we need to spend time on it. It's generally what you would have for these softwares, okay? So it's not so user-friendly because it's an open source. You have some like pre and post processors, but you can use MATLAB. So generally, I mean, you code in TCL or TCL. This is the language that you use for OpenSeas to model. Here is the part where, I don't know, you discretize the section, generate elements, and you get the output, which is, again, you know, in this very ugly format. But as I said, you can use MATLAB and you can plot very nice graphs and everything you need to do with it. So, and you just need an exe file. I mean, even you don't have to compile the code, send me an email, I'll send you the exe file and you can use it. Okay, when we apply this model with all of the inputs, and there's no reason for me to show you like the input files if you're not using OpenSeas, but this is the result we get for OpenSeas. So it's using everything measured, okay? So the inputs are the measured compressive strength, the measured tensile strength, modulus, creep, and shrinkage. So everything is from the experiments, okay? Because we really want to test the model. We don't want to introduce new uncertainties by predicting things from compressive strength, okay? And yeah, we see that it's perfectly capable of capturing the evolution of deflections, of getting the curve right, even the initial and final deflections. Alex says you can try the STKO preprocessor is good enough. Okay, thank you, we'll do that. So STKO, pre and post processor for OpenSeas. And you can, as I did, use MATLAB. So what this model will allow you is to, you know, plot interesting things such as the distribution of strains across the cross-section height in time. And this is what you saw in the earlier image. Like, we are starting from a line that is here and basically rotating around the reinforcement or slightly above it and having an increase in strain at the top fiber over time. And what else? A decrease of the neutral axis. What else you can see? As I said, like, the strain does not change much. It's a very small image. Probably you don't see it very well here, but it's almost constant. And you can decompose concrete strain. So like, this is the total strain, but this is the shrinkage component. You see, like, that it's a lot because, of course, the experiment had like 0.83 per mile of shrinkage strain, creep, and mechanical strain. Even further, you can decompose this, but they didn't plot it here. Like, even creep and shrinkage, you can separate into basic and drying. So you can see the impacts, but for such a low strength concrete, the basic component is not going to be so big, at least for shrinkage. So this is what the model offers you. And, you know, it's okay, but I mean, this software particularly, like, it's academic and you really need to be using it, and, you know, it takes some time. It takes debugging. You're for sure going to have problems, and, you know, not everything is going to work from the first time. Absolutely. So it takes some time. And also to note, like this is now applicable to, you know, beam models, and we're going to get later to slabs, but you know, it's for beam elements, and basically it's not something that we're so interested in. Of course, you can model a grillage, but that's again even more time. Okay, let's see what the Seta method of integration of curvatures has to offer. So here I'm presenting a calculation example for the final deflections at 394 days, and I've separated into 10 sections. I'm going to integrate over 10 sections, and later I'm going to show you with more. Okay, as I said, I need to calculate a lot of things. I need my cracking moment, which is here, like the gross section modulus and mean axial strength. It's 10 kilonewton meters. My maximum moment is almost 25. Okay, so it's pretty higher, it's for sure cracked. Effective modulus here, okay? And now this is the thing that I was talking about. I'm going to use the measured creep coefficient, which is just the creep strain divided by the initial strain. And that's why I'm going to use it with the modulus at the time of loading. Okay, so not going to do that separation into the modulus at 28 days and modulus at loading, because I'm not calculating the creep coefficient. And we see that the effective modulus is, you know, 2.7 times smaller. The modulus ratio is now 23.7, so the, you know, steel modulus over the concrete effective modulus. And now I have to calculate certain geometric quantities. I need the transformed area of the section in the uncracked state. So all of the concrete is active. So I have the area of concrete. I have the modulus ratio multiplying the reinforcement, because the, you know, each square millimeter of reinforcement is worth 23.7 square millimeters of concrete. So I get this area. I need the centroid of the section. This is calculated from the bottom of the section. Okay. So it's going to be, you know, again, just the concrete with its centroid and then the reinforcement with its centroid. The reinforcement always multiplied by the ratio of the moduli divided by the transformed area. So I get it as 161.5. The concrete section is 348. So what this means is a logical thing. The centroid of the concrete section is at 174 millimeters, but the reinforcement in the bottom is kind of pulling the centroid down. So we get 161.5. And the moment of inertia, okay, which is, of course, the moment of inertia of the concrete section, the position component, the area times the differences in centroid squared, and the same thing for the area, which doesn't have its own. So this is the moment of inertia and the moment of area of reinforcement. Again, I introduced here the ratio, the modulus ratio times the area and the difference of the centroid of the transformed section and the centroid of reinforcement. And I get these values. And the numbers are not so important. It's, you know, 1 billion and 1 million something. Okay. I have that in state 1. But I need it in state 2 as well. The lucky thing is here that I don't have any curtailment of reinforcement. So I only need to do this once. The reinforcement is constant along the beam length. If I had, for example, 3 bars and I curtailed the middle bar at some part along the length, I would have to do all of this for also the parts that have only 2 bars. But being a simple example, I'm not going to have to do that. I am going to have to calculate the neutral axis position in the cracked state. And, you know, in the cracked state, I'm assuming linear behavior. So the neutral axis position is not going to depend on the loading. It's going to be constant. So I just need to calculate it here. If I had an axial force, that would not be the case. This is just a ready-made expression, okay, with the reinforcement ratio being a variable, that's all, and the modulus ratio, and it's, you know, 0.393. Okay. So it's 117.9 millimeters, and these are the now new area, which only has the area of the compressed concrete, so only this part. So it's much smaller. It's from 96,000 to 39,000. Okay, the centroid of this section is now 230 millimeters because I only have concrete here at the top and reinforcement here. The moment of inertia is, let's say, 2.4 times less. It's from 1 million down to 450,000. It's going to be close to the ratio, to the effective modulus ratio, 1 plus 7. And the section modulus, the moment of area of reinforcement, is the thing that's going to increase because the centroid of the section has increased. Okay, so it's gone from 1 million to 1,740,000. And this is a logical thing because it's just the difference between the centroid of the section and of the reinforcement. And this has increased from 160 to 230. So I have this, and now I'm going to do an integration and show you how you can do it in Excel in 10 sections, but it can be in 50, in 100, or whatever, and of course, MATLAB or whatever else you need. So I divide the span into 10 sections in increments of 0.1, so it's x over L. I need the moments in each section, and in this case, I have a parabola for the self-weight, and I have this trilinear function for the additional dead load, and these are the equations for the self-weight. Yeah, this is just a general parabola, and this is for the dead load. So, linearly increasing until the third of the span, constant, and then decreasing for the last third of the span. I put in here the final values, and this is, in the middle, it's 24.9. Okay, so going forward, next what we calculate are curvatures in state 1. From load and from shrinkage. Okay, how do we do that? Of course, curvature from load, we saw it's m over e times I, and from shrinkage, it's epsilon times s over I. That's why shrinkage is constant. The curvature is constant because the distribution of reinforcement is constant. Okay, so it's a constant curvature, and this follows the evolution of the bending moment. Okay, and I do that for state 2 as well. Okay. So I see how much the curvature is larger for both. And again, for shrinkage, it's constant because of the constant distribution of reinforcement. And importantly, it's positive. It's in the same direction as from bending. Okay, then I interpolate, sorry for this overlap. I interpolate the curvatures using the Seta distribution coefficient. And here, M max is going to be this M. If I had a higher load that was applied and removed, that would be the moment that I would introduce here. But it's not. So I have these moments going here. For beta, I used 0.5 because I'm calculating the final deflection. And I'm making this comparison. So, I mean, it's 0 basically only here. And already here, I'm cracking. So I have very small parts of the section that are uncracked over time. And I have the mean curvature. Of course, this mean curvature is the load plus shrinkage in state 1, interpolated with the load plus shrinkage in state 2. So in state 2, we see that it's 9.7, and the interpolated is 9.2. So I'm pretty close to the state 2 curvature. Okay. Then I do integration. First time to get rotation. This is the expression that I use, and you see that it just keeps increasing. It's because I'm still not applying boundary conditions. That's why I call it uncorrected rotation. But this is just the expression that I use, and I keep integrating until the end. After that, I do another integration to get uncorrected deflections. Again, this doesn't look good because the deflection is highest at the support. So I need to introduce a correction for the deflection. And it just means getting it to 0 at the end. So the correction is just going to be x over L times the last deflection. Okay, so see the correction here is going to be 38 equal to this. So it's going to get it down to 0. And then when I apply the correction minus the uncorrected deflection, I get this. Now it's symmetrical, and I have the maximum deflection in the middle, 11.96 millimeters, for integrating in 10 cross sections along the length, which is pretty good. And that's it for that. If I do it in 50 sections, like I did it here, and I do it for every time step, I get a bit higher. I get 12.18. So I have an increase of like 2-3%. So, going from 10 to 50 sections, it's not going to bring you more than 5%, at least in this case. And these are the results. Okay, they're again pretty good. there is a kind of different evolution here. What I maybe didn't say, yeah, for the OpenSeas model is that it also considers creep intention, taking it equal to the creeping compression. Now, this is something that, you know, even in experimental results is maybe not so clear. It's maybe even bigger, the creep intention, but it's something that the model takes equal to the concrete, to the creeping compression. But basically, you know, the agreement is good, is there. The result is very good considering the experiment. Again, taking into account that if it were a statically indeterminate structure, if I had any changes in reinforcement, all of this calculation would have to be 2, 3, 10-fold more. Okay. And let's apply a simplified method, and I'm going to do the one formulated by Marie and others. So what this method does is calculate and interpolate initial deflections. Okay, so the interpolation is just done for the initial deflection. Then you multiply that initial deflection by a factor to get the increment due to creep, and you add the shrinkage deflection. So the basis is a bit different, but I'll walk you through the process. And of course, as I said, you use average reinforcement ratios. Again, this example doesn't have anything. It doesn't have compressive reinforcement, no changes in reinforcement, so I don't apply this, but otherwise you would. Dmitry Boris is asking, will be the recorded webinar distributed later?
I suppose yes.
Yeah, for me, of course, the presentation can be shared later, but I guess you will notify the participants. Okay, so you need, because you're doing the initial deflection, you're taking the ratio of moduli in this time, okay, in T0, which is now 8.76, not 23.7. And you're calculating the area of reinforcement. Now it's different because this modulus ratio is smaller, so it's not 96,000, it's 90,000, and all of the values again are a bit smaller because the ratio of the moduli is smaller. But you're doing it in state 1 and state 2, okay? Again, the neutral axis is going to be different because this modulus ratio is different. And also to note here, at time T0, the neutral axis coefficient, 0.263. At time T, which was 394 days, it was 0.393. So that's the shift in the neutral axis over time. This is the area of compressed concrete, and here are the geometric properties that we need. I'm not going to explain them again. You will have them on the slides, and they're written here. Again, the numbers are going to be smaller because, of course, the smaller modulus ratio, smaller area of compressed concrete, and so on. So what you do is you calculate deflections now in states 1 and 2. So from load, you calculate deflection as K, which is a factor that depends on the statical system and the loading, ml squared over the stiffness, again, the modulus at T0, and K is 0.104 for uniformly distributed load. This is what multiplies the moment from self-weight, and 0.107 for loads for two forces in the thirds, for 4-point bending, okay, which multiplies that moment, okay, times L squared over the stiffness. It's 1.53 millimeters in state 1 and 6.68 in state 2. Now here, the Seta coefficient has a slightly modified formulation in that there is an adjustment coefficient K0, okay? And K0 has this formulation. It's an empirical formulation. The point is that it takes into account the uncracked parts of the beam. So the fact is, you know, when you're interpolating deflection, you calculate it in two states and interpolate, but you have to use a single Seta for all the interpolation. And when you're doing it in sections, every section has its own Seta. Now, which Seta do you use when it's a single value? You have to somehow adjust it for the fact that there are uncracked parts. You don't use just the maximum value or medium or whatever. You use this K0 here. which depends on whether the ratio of the cracking to maximum moment is less or greater than 0.5. When they are 0.5, the value will be 0.5. So in this case, because we have a value of, I think, 0.207, we get, no, sorry, the ratio is, 10/25, we get K 0.207, further decreasing our beta, which, because we're calculating a long-term deflection, still goes as 0.5, and we get a high zeta, 0.932. So we get an initial 6.59 millimeters, okay? And then using that initial deflection, we calculate the effect of creep. For uncracked members, it would just be the initial deflection times the creep coefficient, but we have a cracked member, and it's the initial deflection times the neutral axis position, or x over d. In this case, it's this C coefficient. 0.8 times KT, which is something that depends on the reinforcement ratio, that average value, 0.3 plus 100 times rho, times the creep coefficient, and then over 1 plus 12 times alpha, the modulus ratio, times rho prime, which is the compressed reinforcement coefficient. Again, the average, the effective value, which we don't have, so it's 0. And what we get is this, okay? In our case, 2.17 millimeters, the effect from creep. And from shrinkage, it's just a separate value because it's independent of load. It's Ks, which is a coefficient depending on the statical system. So it's 1 for simply supported beams, 0.7 for edge spans of continuous beams or slabs, and 0.85 for interior spans. Then KT is the same coefficient you had here. CS is the curvature from shrinkage. If it's uncracked, it's like this. If it's cracked, it's the shrinkage strain over effective depth, and then 1 over 1 plus 12 alpha rho m. And when you multiply everything here, okay, Ks, KT, strain over depth, and this, which is for us this part 0, 3.52 millimeters. Sorry, Evgeny is saying, hi Nikola, on the diagram you show, we can see that shrinkage do maximum effect to total strain more than even creep. Is it follows that shrinkage is the most important factor for deflections, or I doesn't understand that diagram? Yeah, but it will depend on your reinforcement. As I said, the strain has a high impact, and particularly in this case, because the value was 0.83 per mile and a very small corresponding creep coefficient, which was a bit strange. So when you would calculate, you would get a much higher creep coefficient, and the values would be a bit more comparable. But it will not directly follow the effect of shrinkage on curvature just from the strain. It will follow also from the distribution of reinforcement. So even just by adding a little compressive reinforcement, you will reduce this curvature because you will change the moment of area of reinforcement, because here we only have the tension reinforcement. In this case, yes, the effect of shrinkage is very high. And here you see it also, 3.52 versus 2.17 from creep. But it's just in this case, so it's not just a generalization. But of course, I mean, for slabs, for buildings, you know that curing, shrinkage, because of the cracking that shrinkage can cause, is going to be a very important factor that, yeah, I agree, can be overlooked sometimes, its importance. Okay, and this is the final value, 12.29 millimeters. And we are somewhere in between the Seta and OpenSys methods. We are a bit safer than the Seta method, which is what you want from a simplified method. But yeah, and the computational cost is much smaller. Okay, so these would be like the 3 methods that we saw. Now, which model would you pick? That's for you to think, for which applications, and most importantly, why? And another question to have is, what about input parameter uncertainties? So in design, you would just have your concrete class and you would calculate tensile strength, you would calculate the modulus, creep coefficient, shrinkage strain. But in reality, these will easily be, plus minus 30%. As I told you here, for the creep and shrinkage, take these values and calculate them by model code. You will never get at the same time a high shrinkage and low creep. coefficient, okay? So in reality, they can differ. And what are the effects? And here I just made a small sensitivity analysis, but for this particular example. So I increased or decreased tensile strength, modulus, creep, and shrinkage by plus minus 30%. And you can see the effects. And here they don't seem so big, okay? I did not express them in percentages, but just as deflection values. But they are huge for slabs, for example, which, as I said, usually their service load is close to the cracking load. And imagine that, you know, your tensile strength shows you, when you're calculating your predicted tensile strength, shows you that the slab will be uncracked and a very small deflection. In reality, you don't cure the slab, there's a lower humidity, or you don't cure it well. You get a lower tensile strength and a lower cracking moment. It cracks and the deflection jumps because now you're interpolating between a cracked and non-cracked slab, and the difference is huge for a small difference in the parameter value. So very important to take into account when you're dealing with slabs and in-service behavior close to the cracking load. You know, do a sensitivity analysis to at least like tensile strength. If it's plus minus, you know, you have in the codes the lower and upper characteristic values, which are 30% different. Do a calculation to check, you know, at least where you are with this. And not to mention creep and shrinkage. I mean, you have also in the codes characteristic values, and the differences are even more than 30 plus minus 30% because they can be huge. Okay, and then to think about like an effective strategy for decreasing deflections. So, you know, is it increasing concrete strength plus? Probably not going to be such a difference. As I said, the modulus is not going to change. Yeah, are you going to add tensile reinforcement? Okay, is that going to help? Or are you also going to add compressive reinforcement? You know, if shrinkage is the problem like here, adding an equal amount of compressive reinforcement will eliminate the curvature from shrinkage completely. Okay, so, you know, how much does that cost? Is it effective? How are you going to distribute that reinforcement, and so on? Okay, I'm wary of the time, and sorry, but we're wrapping up here. I'm just going to spend 2 slides on challenges ahead. So what about the elephant in the room? I've been talking about, you know, slabs, and all of these models look pretty simple for beams, okay, for linear elements. But what about bidirectional elements? How do you calculate deflections for them? You know, that's the million-dollar question so far. And there isn't a straight answer, at least not for now. What do we do with flat slabs or edge-supported slabs, slabs supported on beams? Okay. For, you know, 50 years now, the answer has been, well, approximate them with strips. Okay, so, you know, an edge-supported slab, take a strip in one direction and its tributary load, depending on the support conditions, and calculate the deflection of this. This is like really a crude approximation. So if these were beams here and the slab didn't have continuity, this would be a simply supported beam, but you would have to calculate how much load falls on this beam. So if the spans are equal, that's half the load in each direction. And you say, okay, simply supported beam under half the load, that's it. But of course, we know that there's the effect of the other direction. The torsional stiffness of the beams in the other direction is what gives also stiffness to the bending stiffness to this direction, which isn't taken into account. And it's even worse when we get to flat slabs, because there, you know, the recommendation is, you know, take strip in one direction, then take the strip in the other direction, and, you know, superimpose the deflections. Take a strip over columns, and in the other direction strip through the middle, and combine these 2 deflections. And then do it vice versa. Do it this column strip and this middle strip, and then the average of these 2. It's really like crude approximations. The goal is, can we do better? Okay. And I think yes. And the task group 2.1 is working on it. Even just yesterday, I had a meeting with Professor Tony Marie and Luis Torres here from Spain, and we are, you know, testing some methods, some approaches. What we want to do, what I think would be a very good way, would be to use linear FEM results. So most of you in design, you'll be using a linear FEM software. To a lot of people in the audience, this will be familiar. This is from a Serbian program called Tower. So, it's shell elements, linear analysis, black box, very simple, but you get some elastic deflections, okay? How can we use these elastic deflections to somehow transform them into deflections in the cracked, uncracked state and, get a prediction of the long-term deflections? We can go into the direction of somehow transforming the FEM deflections, just based on transforming stiffnesses. This would be the stiffness in the software, and this would be what we calculate for a section here. But this is not taking into account the torsional stiffness. It is taking into account in the software, but not here. So, we have to look into that. And what about shrinkage? How do we add shrinkage? Because it's very difficult to model in this software. Is it temperature? Is it somehow calculated? But, we're looking into that. And we're missing experiments. There are not a lot. So we're hoping that, and this is also an open invitation, if you come across some literature of experiments on bidirectional slabs, please send them my way. Or we'll have to go into nonlinear finite element parametric studies and then calibrate the models on those. But this is something that we're looking into, and hopefully it can be a contribution for the new model code. And as I promised, like here, you have the references that were throughout the presentation, so you can look at them. And with that, I would conclude my presentation. I would thank you so much, and I'm sorry for the time, but I don't know, Dmitry, if we have. I'm completely open for a Q&A of as long as there are questions.
Yeah, I think we have, and actually in the question sections, we have two unanswered questions. Can you check it?
Okay, yeah. Evgeny says, we have in fact 4 times more flexible RC structures. What did you mean? Did you talk about all structures with creep influence, or did you mean something more? For example, changes in concrete production technology, construction. Yeah. All of these, I'm saying that before you would have larger safety factors, which would lead you to using thicker slabs, like of greater depth for the same load when you would design them. You probably use more reinforcement. Because of the large uncertainties, curing would be longer, shoring would be longer, loading times would be later, and all of this would result in a much stiffer structure. Okay, and now the pressure is to have larger spans, LD ratios. Let's just consider it in LD ratios. Now a slab will easily have, LD 25-30. I'm not sure it was like that, 50, 60 years ago. That's what I'm just saying, that L over D has a tendency to increase. That's all. Okay. Are these methods applicable for GFRP reinforced members? Can we take into account creep of GFRP reinforcement with these methods? So there are even separate, if you look into, I will just point you to bulletin 92, because this is not my area, but there are specific sections on GFRP. So I'm not in the position to directly answer this, but I would just direct you to the FIB bulletin 92, because I know it has sections, and probably in the new model code also will be specific sections for GFRP.
Yeah. So the new question in the chat.
Okay, sorry. Let's see. Greater strength of concrete, greater width of crack opening, and this does compressive strength of concrete higher than you need is bad for. No. It's not the intention to convey that it's bad. It's just that it's causing us to think more about serviceability, and I think this is a good thing, because then we are developing our methods, because the methods have been in some aspects undeveloped for some time. The tools are now there. Finite element modeling is becoming more commonplace and more easy to use. So as you see now, we're looking into bidirectional slabs. So it's a good development, and we will overcome also this challenge, and then we will catch up with ultimate limit states. Okay, Albert says, yeah, deflections in FRC members. Thank you, Albert. Albert is Albert de la Fuente that I was talking about at the beginning. So yeah, as I said, that is the topic that our research group is looking into. And yeah, because there is going to be something very different, you know, this interpolation, it's not the same when it's fiber reinforced concrete, if it's a hinge, if it's a single crack, if, you know, the distribution is different, if fibers creep or don't. So yeah, this is going to be, and hopefully these structures will be more and more used. And we've seen the group has had experiments on flat slabs with, you know, no reinforcement. So what about deflections for them? So definitely, yes.
So there are no new questions.
Oh,
no.
Will there be any new workshop sometime soon? Yeah, this is, I mean, well, I mean, Dmitry will say for the Russian group, for the Serbian, we are talking and have been thinking of something similar. So, you know, our idea for some time has been to actually emulate what the Russian group is doing, which is for me very interesting. The journal club, you know, reading articles from structural concrete. So this is somehow first on our list to make an online somehow presentation of some papers from structural concrete. Hi, David.
Oh, David, join us again. So
yes, well, I was listening. I just wanted to congratulate Nikola. Great presentation.
Thank you.
Very,
Thank
very
you,
interesting. I hope we can share it online somehow in the YouTube channel or something like this, because it's great.
For sure.
And great initiative, Dmitry. Very, very nice.
Yes, today we tried it the first time, and I think that we have succeeded in this. And I heard a lot of interesting information, and I think that Russian group will analyze it and try to compare it with Russian models. It will be very interesting, and probably we can share with our experience soon. But it was the first time, and I think we schedule new webinars soon. And I think our groups, Serbian groups, and in the international way, we can make such events and new circumstances. I think it's the only way for the next couple months, or maybe more. I think it's a good event, and it was a good event. And thank you, Nikola.
Thank you,
it was really great presentation, and thank you that you were the first keynote speaker. And
thank you.
We'll
thank
go
you.
on.
It was really my pleasure, and yeah, I hope to attend now the second event like this. And yeah, thank you so much.